So, now we have two equations. So, in CCM, V out equal to D times VDD. In DCM, V out equal to 2 over 1 plus square root 1 plus 4k over d square. If I want to draw this, so if this is your I load, it will look something like this. Okay, this will go to VDD and this is nothing but V out. So, what will be this? D times VDD. This is your CCM and this is your DCM, and this curve will follow what? V out equal to 2 over 1 plus square root 1 plus d square into VDD. For constant V out and Vn, which means V out over V in equal to 2 over 1 plus 4k over d square should be constant, which means in order to, so what are the variables? K and D only, so 4k over d square should be constant. And what was the K? To L over RL TSW. So, this implies 4 over d square into 2L over for fixed L and TSW. If RL is increasing, in order to keep this constant, what should we do? Duty cycle has to decrease. Okay. So, for the same V out by V in ratio, if it is in the CCM, if you are getting some duty cycle, when it enters into the DCM, so duty cycle will become function of your load current. In fact, a strong, you can say strong, I mean in CCM also it is a function of a load current, because your conduction losses will increase. So, you remember the delta D term we required, but that will be very small, maybe 1% or so. But here it has to change by square actually. So, it is a very strong function of your load current. So, the duty cycle, so let us say in the DCM your load current becomes half. So, D has to change by 0.25 times, 1/4 of a current duty cycle in order to regulate. So, if you keep reducing, what will happen? Eventually it may go into 0, and when the moment it goes into 0 duty cycle, what would happen? Your converter will switch off, huh? Your loop will break, it will become as good as non-linear, huh? So, that is why in most of the converter we limit the on time. D equal to 0 means on time is 0, huh? T on is 0, but we never allow that condition in a steady state. During transient you may, and it will recover, because during transient you have to either sink or source very high current depending upon whether load is positive or negative. So, you can allow actually to turn on the bottom or low side or high side FET for a longer time. So, you can allow like 100% or 0% duty cycle, but in the steady state if you allow that, then your loop will become non-linear and as good as open loop actually, it will break. Your op amp and everything will saturate in that case. So, that is why for linear operation we limit T on to T on min. So, some minimum on time which is sufficient to turn on your, because those switches will have some rise time, fall time, then you have some dead time. Okay. So, this T on should be at least more than that, otherwise your MOSFETs will not turn on at all. So, whatever the propagation delay you have in that path, this T on should be more than that, and most of the time depending upon switching frequency we decide this. If a higher frequency you may have to limit at maybe few, let us say 100 nanosecond or so for lower frequency. For higher frequency you may have to limit this maybe tens of nanosecond, 20 nanosecond, 30 nanosecond. Okay. So, what would happen in that case? Let us see. So, now your T on, so D equal to what? What is D? T on over TSW, and for minimum it will become T on min over TSW for max load, or not max load, for higher load I would say, for high load. When I say high load, high RL actually, do not get confused with the load current end, or lower high load. Okay. So, substitute this to which means your 4 over, now D square will become T on min square multiplied by TSW square 2L over RL TSW. This has to be constant, which means 8L over T on min square TSW over RL. So, T on min you have already fixed. So, that is a constant term. This is constant. So, which implies your TSW over, and RL is also fixed because that is an inductor. So, you do not have any control on that. So, TSW over RL should be constant in order to regulate the output. Correct. So, if RL is increasing, then should increase, or FSW is going down, which means your FSW is what? Proportional to I load. So, for DCM operation, this is the condition. If you don't meet this, you cannot regulate the output. Now, if you remember, go back to your losses. At light load, your switching losses starts dominating. So, we have to reduce the switching frequency in order to improve the efficiency or reduce the switching losses. So, if you operate in DCM, you automatically get that actually, because in order to meet the regulation, your frequency has to be reduced. Okay, but if you operate in CCM, then you don't require this condition to meet. Then in order to reduce the switching losses, you have to reduce the frequency forcefully actually. Here if you operate in DCM, your loop will automatically reduce your switching frequency for DCM operation. And this is called nothing but your PFM mode. Pulse frequency modulation. So, you modulate your frequency with load current. So, or you skip the pulses effectively when you start skipping the pulses of your PWM. So, effectively on an average you are operating at lower duty cycle, lower switching frequency. Okay. So, that is called pulse skip mode. We will talk about that also, PSM. How we implement this will come to later. So, no, you don't operate in the PWM mode actually for this. When you hit the T min, you don't have any room to change the duty cycle. Huh? So, the only option you reduce the switching frequency, and this means, and T on is fixed. So, in order to reduce the switching frequency, what do you need to do? You have to increase T off. Okay. So, T on is fixed, T off is increasing. So, switching frequency will automatically reduce because you do not have any room to further reduce T on. So, your control loop will change actually. It will from PWM, it will go to PFM mode, and earlier your control voltage was controlling the duty cycle. Now, your control voltage has to only control the T off time rather than controlling the duty cycle. So, that is the difference between the two, and then the T off should be a function of your load current, which means lighter the load, the T off needs to be extended for longer duration. How to implement will come to later, but this is what you require for DCM operation. Otherwise, your output will not be regulated. If you don't worry about the efficiency and all those, then you can forcefully operate in CCM. So, what is the drawback here? Once you start reducing at lighter load, you are reducing the switching frequency. What is the drawback? Output ripple, will be higher. Correct. I mean, effective filter. I mean, yeah, your filter cutoff is you place at some. Now you have moved, so the suppression in the ripple at lower frequency will be lower. So you will see a larger ripple. That's why in the PFM mode, your ripple is more compared to the CCM. So sometimes you forcefully operate in CCM even at light load if you are concerned about the ripple for noise sensitive applications. If you cannot afford a larger ripple in the output, then you have to forcefully operate in CCM. Then you don't need to turn off this bottom FET here. okay, when the current goes negative, which means you allow the forcefully allow the negative current intentionally to keep it operating in the CCM, so that your output ripple will be low. And that is used so many places, like in the displays and all those, we use that for noise sensitive applications. Other thing is that if noise sensitive application, if you care about the noise band, the frequency band. So let's say in CCM you fix the frequency at 1 megahertz. In PFM it may enter let's say a few hundreds of kilohertz or even tens of kilohertz, and especially for audio application you don't allow any ripple below 20 kilohertz, because that is the audible tone. So that may interfere with your audio frequency. So most of the time we first thing we try to keep it below 20 kilohertz. So which means if you further reduce the load and you have to reduce the switching frequency, then you cannot reduce the load beyond that. If your load is reducing, then you have to put the dummy load actually at the output, so that your frequency doesn't fall below 20 kilohertz, okay, or you forcefully operate in CCM. That these are the two options you can do. And if your, let's say, application cannot even afford anything below 1 megahertz, then you don't have any option. You just operate always in CCM. You don't go in DCM, and that will come at the cost of your efficiency. So there is a trade-off between noise and or output ripple and efficiency in that case. Okay.